Hey, Dr. B here, and let's do several rate problems that mostly deal with transition states and activation energies. For the reaction of hydrogen with oxygen to make water, if you line up the reactants as shown here, it suggests an activated complex where all the bonds are simultaneously breaking and forming. Is this the actual activated complex? Probably not. These things oftentimes go stepwise, but it's a good thought experiment to see how you might be able to come up with one combined activated complex. Let's draw it using dotted lines for each partial bond. Now, you know the bonds that are breaking will be identical to the bonds that are forming, sadly, if you're just using dots, but it'll give us a good idea. So just change all your reacting molecules, that's the bonds that are breaking, as dots down the middle, and those four bonds that are forming, which are all hydrogen to oxygen, vertically there, and that could be an activated complex right there. For the reaction of chalk with hydrochloric acid, the reaction is found to be exothermic. Predict if the rate of reaction will increase, decrease, or remain the same when you make the following changes. So this is rate of reaction. I always think of the memory device STIC, S-T-I-C-C, and I think about what would happen. If you ground it into finer particles, that should increase the reaction rate because you can have more frequent collisions with the chalk. If you add water to the reaction mixture, you're going to dilute things. This should slow it down because you'll have more frequent collisions, for example, with the solvent, and fewer collisions per unit time with the reactants. If you heat things up, that should increase the reaction. You're going to get more frequent and more powerful collisions, though you're not necessarily going to get all the desired reactions when you are having more energy and there's more activation energies that you can overcome for various reactions. Calcium chloride's removed from the reaction mixture as it's formed. That's a wonderful way to increase the rate of a reaction, since you no longer can have collisions with the product that would lead to the reverse reaction. And if you add a catalyst, that definitely helps by lowering the activation energy. And it's usually also added that by definition they must be going through a different mechanism since it's interacting with the catalyst. Catalyst is discovered that lowers the activation energy by 75%. Let's draw an energy diagram that matches the data. Simply draw a hump that is 75% lower. At 150 K, some diatomic substance is decomposing with a certain rate constant, and at 700 it has another rate constant. So therefore we have two temperatures, two rate constants. They want the activation energy. Wouldn't it be nice if we had the Arrhenius equation rearranged so we're solving directly for activation energy? That's what I always give my students since it's the most common question. You'll never see it in a textbook because they force you to rearrange, which to me seems silly. So there it is in its rearranged form, and now all we have to do is plug in. The low temperature is 650, so that's our T1 with the corresponding activation energy. Those should be exponents. And so just figure out what K1 and T1, K2 and T2 are. Make sure you're using Kelvin for your temperatures, and then plug it into the equation. And you'll see that, it's not given, so I don't know what that activation energy is. So we'll leave it for the students to do the final calculation. A reaction rate doubles when the temperature increases from 25 to 40. That actually does tell us both K values. It's going from 1 to 2. Any number like that would work. 2 to 4, 4 to 8, so 1 to 2 is fine. And that is at 298 and 313, I believe, Kelvin. And let's find the activation energy. Once again, we plug into the rearranged form of the Arrhenius equation. There's our 1 over 2. There's R, which is the energy form of R. And be sure that you realize that you got to use Kelvin because it says to. And it's going to spit out joules because it says so. And this will give out 35,000 or 35.8 kilojoules, 35.87 kilojoules for each mole. The activation energy for the isomerization of cyclopropane to propene is 274 kilojoules per mole. By what factor does the rate of reaction increase as the temperature rises from 500 to 550? Well, you could rearrange it for solving for the natural log of K1 over K2, but be careful if you have to flip it over at the end. I'm pretty much locked into this form of the Arrhenius equation, so I'll do it that way leaving this part right here unknown, and then I'll solve for it, and then I'll think about whether it's right or not. And to do that, I won't get too picky. I'll just say that if it gives me a number that's less than 1, I must have it upside down, right? Because if you're heating it up, it should give you a higher K value at the higher temperature, so it should give you a positive factor. Okay, so we have all our data. There is our two temperatures. So I think we're dealing with 773 and a little bit higher. Make sure you're using Kelvin. There it is, 773 and 823. Always make your T1 the initial conditions, that's 500, and T2 the little hotter conditions. Make sure you have K1 and K2 corresponding to it. In this case, they're still just letters. Solving for this chunk right here, we find that it's equal to, well, we're almost there. And now we have the natural log of it being equal to a number. So we take e to that power to solve for it. We're getting into some slightly higher math here. And when we do that, we find that K1 over K2 is 0.075, which is messed up because it's supposed to be faster when it gets hotter. So clearly we have to invert. It's K2 over K1, which is what we want. That gives us a value of 13, which seems reasonable. The reaction gets 13 times faster when you heat it up 50 degrees Celsius. And that's pretty close to the doubling the reaction rate for every 10 degrees that you increase. Okay, so that's several questions dealing with rate of reaction.